Hello, this is just a quick explanation of the Maxwell-Boltzmann distribution, just to clear up any queries that you may have about it. A Maxwell-Boltzmann distribution is just a diagram that you'll draw in an exam to explain the speed of molecules in a gas during a particular reaction. It won't be a qualitative answer, you won't have to know answers, you will just be having to draw a sketch of it. So for example, the question might ask you to draw a Maxwell-Boltzmann distribution for a gas at temperature T1 and then another one for temperature T2 where the temperature T2 is greater than the temperature at T1. So the first thing you need to do is to draw your Maxwell-Boltzmann distribution for T1. That can go anywhere on the diagram, on the axes, as long as it looks a little bit like this and you've labelled it T1. You can then add T2. So you start off at the same place. Now T2, the temperature is increased, so you shift it to the right. The top of the curve will not be as high and it'll be a little bit flatter, and the end will be higher, and you label that T2. The area under both graphs will be the same. That is the whole point. It's the same gas, so the area under the graph should be roughly the same. It doesn't matter if your diagram it's not exactly, it just has to look like it's going to be the same. Then in order to explain what's happening and why the rate of reaction is increased when you increase temperature, you need to put in where activation energy is. Again, I don't have any numbers on this graph, so I'm just going to put activation energy in somewhere sensible, so I'm going to pop it here and then label it EA at the bottom there. And then the area under the graph is the number of molecules that have reached your activation energy. So for the green graph, going to be like this, and then for the red graph it's the area under here. So for red graph, which is T2, the higher temperature, the area under the graph is much higher than T1, so there are more molecules reaching activation energy. So that's a good explanation of why T1 has got a bigger rate of reaction, faster rate of reaction. So you can do the similar one with a catalyst. So with a catalyst, you put your Maxwell-Boltzmann distribution in. Look exactly the same as our last one. Nice, just do a sensible one, looking a little bit like that. And then you can put for your catalyst. Now remember, a catalyst changes the rate. It changes the activation energy. So what it does is it lowers the activation energy. So for catalyst, without a catalyst, pop it here and then label it EA no catalyst. And that's the area under the graph there. So when we put a catalyst in, what we're doing is we're shifting that line towards the left. So this is with a catalyst. And as you can see, you have increased the area under the graph, therefore there are more molecules reaching that particular activation energy. Don't worry too much about the numbers, and certainly don't worry about the Zartman experiment. You're not expected to know that. That's something you'll come across at university. Keep it nice and simple. The questions about Maxwell-Boltzmann distribution are fairly simple. You'll also come across it in biology as well. So it's a good one to remember and learn. But again, don't get yourself bogged down too much in it. Just keep it nice and simple.